Good afternoon. This is CIVE 634, Surface Water Hydrology. I'm Professor Victor Ponce at San Diego State University, and today is our class number 61, meaning the 6-week first lecture of 2. And the subject today is Introduction to Hydroclimatology. This morning I made a switch here a little bit. I had E2 as E1 and E1 as E2, and I switched it. I like to start with E01 first. Why is that? Because it gives the flavor of what we're going to be talking about here. The issue is that hydroclimatology is considered to be a subject of hydrology, and it is also a subject of meteorology. And traditionally, the physical sciences have been all about Cartesian coordinates, x, y. If you have an X, you can have an effect by looking at the Y. This all started about 300 years ago with, I believe it was the Frenchman Descartes. I believe that's the pronunciation. I don't know French, so I can't pronounce French names, but he invented or he developed the concept of XY coordinate system, which reflects a cause effect. However, we find that when we look at broader issues that include life on Earth and so forth, it is hard to put everything on an XY context, as it will be shown here when I discuss the Budico approach to hydroclimatology, dated 1953, and later on, Mr. Budico was a top Russian hydrologist, and he had a lot of publications. I believe I read one that at one time when I was, 20, 30 years ago when I was studying all this stuff. And I thought that book was totally great. I read it a couple of times, and I recommend it to people that I care about, that they learn the reading of Budico's famous work, which I believe it's called The Evolution of the Biosphere. That is one of the top works of Mr. or Dr. Budico. At any rate, what we're going to start here is by showing you a concept which we have referred to as cybernetic concept of hydrology, meaning there is no cause effect in here. It's cybernetic, it's biofeedback. In other words, when you say cause effect, it's entirely opposite to cybernetic and vice versa. So let me just start the video. There is a raster, or rather a vector in here, but also a raster. And I'm going to start with the raster, skip the vector, and then move on to the next paper. So let's get started here. This video is called the ARS Lab in Tucson. ARS Lab in Tucson. You guys know that ARS means, in our jargon, Agricultural Research Service. They are the ones that developed the USLE equation, which we cover in sedimentation engineering. So I'm going to be talking here, it's a 4-minute video on the ARS Lab in Tucson. See what's in it. Why should I talk about that at this point? Fascinating story, by the way. To the left is the Budico Model, which I will endeavor to explain in more detail later on. Very complex subject. In November of 1994, an international symposium was convened in Tucson, Arizona to honor Dr. Ken Renard. Ken Renard retired in November 1994, and there was a big deal or a big event about his retirement. He had worked with the ARS since the late 50s, about 30 years. He rose to become the head of the lab in Tucson, the ARS lab in Tucson, hydrology lab. So they had a retirement meeting and conference, and I was lucky, I guess I could say, everything is lucky for me, to attend the conference. I was together with Mr. Lohani, and we had written this paper, and I thought I was just going to go out there. It was a good trip, and we wanted to go to Tucson for some reason. I had done a lot of work in the Santa Cruz Basin in the early middle 80s, and I just wanted to revisit out there in Tucson.
On the occasion of his retirement, Ken had directed the USDA ARS lab in Tucson, presently the Southwest Watershed Research Center, for more than 3 decades. In one of the meetings, Ken confided to his audience
the ARS lab in Tucson runs the ARS Walnut Gulch Experimental Watershed, which may well be the most instrumented experimental watershed in the U.S., in the world, certainly in the U.S.
The lab,
I believe it's 53 square miles, if my memory serves me right tonight.
Had been originally established.
Look at the number of rain gauges and the number of flumes for measuring the discharge.
In the early 1950s, with the purpose of evaluating how established in the early 1950s.
I'm backing up in here because I interrupted, and you may have not understood what I'm saying there. It's very important. Note what I'm saying.
With the purpose of evaluating how upstream conservation practices would affect downstream water yield.
So the ARS was trying to conserve upstream. Yes, conserve water means add some vegetation. And the vegetation was going to take some water because vegetation always uses water.
USDA had programs with local ranchers to improve conservation practices, but downstream users objected to the programs because prior appropriation water laws entitled them to water produced upstream.
This is interesting. So they were going to try to help restore the watershed upstream, but the people downstream, the ranchers downstream, argued that they own the water because the water is coming from upstream, and as long as their water and the water, they felt that they own that water because it was surface water in the United States. Every iota of surface water has already been allocated, and this was in Arizona. So it was a complaint, argument, and ARS, the federal government and ARS decided to go back to their notes, their books, and they realized that they had a lot of hydrology that had been put together in the West, in the eastern United States, eastern and Midwest United States, as development came through. But they felt at the time, and this was the middle 50s, that they were lacking knowledge on semi-arid hydrology. And this is semi-arid. So what did they do? They decided to build a lab to put it together, hire the top people in the United States, doctors, PhDs, that would study this.
Thus, the lab's original mission was to quantify the cause-effect hydrologic phenomena in semi-arid regions.
The cause-effect hydrologic phenomena in semi-arid regions. That was their original charter, 1955, of the ARS lab in Tucson. By the way, ARS has a lot of labs. I don't know how many, maybe 5 or 10 throughout the United States. Tucson lab's not the only one.
It soon became apparent that factors applicable in more humid areas were not applicable in drier climates.
They found out that the formulas that they had for humid areas somehow didn't work. And as a matter of fact, that was very much documented. I wrote a paper back in the middle 90s about this precisely. And there was a problem that the hydrology of humid areas could not be applied outright to the drier areas. So since the United States was moving into the western areas, they had to develop the science in order to use properly the western areas. And it was standard or normal that they should do this.
Much effort was spent on quantifying the various components of the hydrologic cycle in semi-arid regions. Eventually, the original mission was altered to
much effort was spent, but they ran into a wall. They couldn't do it. They felt that it was too difficult for them to do. And I think I mentioned, or I was talking to somebody out there, and they said that the correlations were coming out very low. They tried to correlate this with that, and the correlation just wasn't there, too low to accept. So then, in very characteristic fashion, what they did is that they figured out what else to do, and they started doing it. So that's what Ken Renard told me when I was there. I'm not inventing anything here.
Include erosion and sedimentation, watershed modeling, and remote sensing.
So they got into rainfall modeling, watershed modeling. They're very good with watershed modeling. Remote sensing was coming up at the time, very important. Erosion and sedimentation is always there. You cannot stay away from it. And therefore, the lab changed quite a bit its mission over the last, since it was formed, 1955, it's 60, 65, 67 years. So now they're doing all sorts of stuff, and they're very good lab, but they are not necessarily focused on the original mission.
A clearer picture of the hydrologic cycle across the climatic spectrum has emerged in the wake of the ARS Tucson experience.
Across the climatic spectrum, what is that? That's a term that I developed back in the year 2000. We wrote a paper on droughts, and we came up with this classification that you see in here, and we are going to talk about extensively later on. We decided to do this chart, and I will explain each one of these numbers later on and how we develop them. But the important thing is across the climatic spectrum. I kind of developed that term because the classification of Köppen was not enough. It was too complicated. It covered everything, but yet it was not simple enough. It's too complex. Köppen's classification of climates. So we simplified it, and we decided to do it this way. I had experience both in very super arid regions, such as the coast of Peru, where I was born. And I also had been to very wet places like the Amazon, and for that matter, India. I was in Patna, out there in eastern India for a month with an assignment back in the year 1994, I believe, 1993, 1994. And I learned firsthand what it is to live out there in the middle of a jungle. Some people call it hell because it's so green, and I guess you could say it's a pain. People that are not were not born there find it difficult because of the problem with mosquitoes, bugs, all sorts of bugs out there. You gotta have be used to it already to be able to live out there. This is Eastern India, Patna, Bihar. By the way, you may not have heard of those names. Uh, I actually missed going to Cherrapunji in Assam. And the reason was that I had been scheduled to go out there and do some visits, some inspection, but they won't let me in because I didn't have the right papers. You know how it is. You have the right papers. So fortunately, I guess I didn't get to go Assam. Fortunately, I say because if Patna was bad, Assam was going to be worse from the standpoint of the elements out there. Okay.
It is now increasingly apparent that the behavior is not so much one of cause-effect as in the conventional hydrologic cycle, but rather one largely controlled by cybernetic, that is, biofeedback processes.
Okay, let me give a little bit of history here. In 1993, when I was in India, 1992 and 1994 actually, I researched basically the Eastern thinking on hydrology because the Indians were kind of in the middle of it and so forth. So I came back with Livovich, Budico, right? And I decided to study it, and I did study it for a couple of years, which led to the paper that we're going to discuss right now. And I thought I had come up with something relatively new, at least for Western thought. But in 1995, I went to Texas, San Antonio. There was a meeting out there of ASCE, and what did you guys think I ran? I ran into Professor Eagleson of MIT and his associates. I believe it was either Entekabi, Professor Entekabi, and or his associates, his students, and they were talking and presenting papers on the modification of the Budico model. So that was MIT. So I figured that they had already accepted it and were looking into it as a good thing to research. So basically we just ended up doing the same thing, only that they, of course, have a lot more resources than I have. For one student that I have, they probably have 10 out at MIT. And those are the good ones. So MIT basically led in the middle 90s the, I guess you could say, the incorporation or the Budico approach or the Budico models to the United States and therefore Western practice, hydrologic practice. Anil Lohani was one of our exchange scientists from India, and Pat Houston was one of our students. I think Pat graduated in 1995. He went to work for one of the big companies, CDM, I think, but now CDM, I think it has a different name.
Anthropogenic reduction.
I came up with this chart. This is an interesting, fascinating chart, actually. Based on the work of Budico, I was able to define three coefficients. The runoff coefficient, I believe this is an R. It's not, it looks like an F. It really looks like an F, but I think it's an R. That's probably a typo in the graph. This is the discharge coefficient, runoff coefficient, and recycling coefficient. So we were able to define these coefficients in terms of the hydrology as defined by Budico's hydrology, cybernetic hydrology. It is cybernetic. And the thing about these coefficients, as we will see later on, is that they add up to 1. So across our climatic spectrum, 125, 250, 500, all the way to 4,000. Interestingly enough in here, at the time, it was early for me, and I just put the numbers in there, and I felt that that was the way I was going to calculate them. And I did make some calculations, and I came up with this graph. So it's not pulled out of the air. It's based on conceptual hydrology of Budico, okay? But I made a mistake, or rather, I divided in units of 1,000. I'd say 1,000, 500, 250, 125. Why did I do that? Because at the time I did this, I had read a couple of books of geography, and that's what they were saying, that the 1,000 was central, it's a good number, and then you can divide it and do it this way. So I used these numbers for the Budico methodology. Little did I know that afterwards, later on, 3 years later, actually it was only a couple years later, in the year 2000. This was done in the year 1995. The other paper came out in 1998 or 1999. I decided that this was not the right approach, that the fulcrum here, the value in the middle, was not neither 500 nor 1,000. It was 800. We picked 800, and I'm going to discuss that later on in much detail. So anything below 800 was going to be arid, and anything above 800 was going to be humid. So that is what we said.
Reductions in evapotranspiration are likely to trigger local climatic changes which have the net effect of reducing runoff. Likewise, increases in evapotranspiration could bring forth increases in runoff.
So in other words, we're saying in here, let it be known that there was an argument out there that said that if you increase evapotranspiration, we're going to lose our water downstream because it's a cause-effect thing. Our argument, as well as Budico's and Eagleson and Entekabi and all the other people that have followed Budico, is that no, that nature doesn't work that way. Nature never works cause-effect. Life is all based on cybernetic mechanisms, meaning the cause becomes an effect, and then the effect becomes the cause. It's a biofeedback. Therefore, we argue, and I think it's a good argument, that if the number of plants increase, the number of runoff is also going to increase. It's not going to decrease, it's going to increase. In other words, you're going to shift from one state to another state. Gradually, of course. It will take some time, but it will happen. That explains a lot of the findings that we have had over the years. That explains why moisture in an arid area may be 15 millimeters, and in a wet area may be 50 millimeters. So if it's all matter of moisture in the air, it would rain in the Amazon 3 times more than in the Sahara or some similar case. And that's not the case. The amount of rain in the Amazon is probably 100 to much more than 100, perhaps 200 times more than the Sahara. So how does that happen? Through biofeedback processes. And that is one of the reasons why ARS could not figure out what to do, because they were looking for cause effect in the 50s and 60s, and they couldn't find it. And that effect or condition, by the way, has been documented in the literature. Okay, so now what we're going to do is I'm going to not read, I'm going to show you this paper. I expect you to read it. It's very comprehensive, very detailed. If I had to read it for you, it'll take 2 hours. So I'm not going to do that. I expect to get to EO6 today. So we're doing well. But I do want to introduce this concept and briefly talk about how Budico's model is put together. And the paper is called Surface, Albedo, and Water Resources. Hydroclimatological Impact of Human Activities. I should tell you that when I was in India, back in the year 1994, I ran into Professor Balek in the mess room of the hotel. Actually, it was not the hotel, it was the, I don't know what they call it out there, but they have a typical name, like it's not a hotel, it was a place for scientists, like a room or building. And I ran into the Professor Balek in the mess, and I had heard about Balek because he had written a book. He is from Czechoslovakia, by the way, or the Czech Republic. Now, there's no Czechoslovakia anymore, Czech Republic. At the time, I think there used to be. So the Czech Republic, and we struck a conversation with Balek, and I made myself a purpose to get his book and read it, because Balek had written a book that is called Tropical Hydrology. And I felt that as far as tropical hydrology, I was knowledgeable in terms of having been there, but not having studied it. And I knew that Balek was his book was going to have a wealth of information on a hydrology that I was not aware of. And since I wanted to cover all hydrologies, then I said I want to read his book. So I got his book and I read it. And it was good that I read his book, because it opened my eyes on many things that he knew and I obviously had not known or didn't know at the time. So with Balek's book, I reinforced my concept on looking at the whole thing from super arid to superhuman hydrology, from 0 to Cherrapunji, 12,000 millimeters per year of precipitation. Okay, so I have in here the paper, and it is customary in our class. I have already converted the paper to HTML form, so we can look at it and we can increase the size a little bit if we want to. Okay, so let's take a look. I'm not going to, I mentioned to you, I'm not going to get into the mathematics. I don't think you like the mathematics either, or the physics. But I'll talk about various issues. The thing about Balek's book was that he made a big deal about albedo. And I, at the time, did not know too much about it. I had written the book, and in my book I covered albedo, but superficially. But he had made a profound, in-depth study of albedo, so albedo became very important for me. That was in 1994, which led to this paper, which was published or written in 1995, actually, and then published in 1997. Okay? So, the objective of this paper was and is to figure out what is the hydroclimatological impact of human activities on albedo, and what does that cause to water resources? Very important subject, and it had not been covered up to this date in the literature. So my paper sailed through the review process. People liked it. A year later, I got a job to do some teaching in Utah, and the gentleman that hired me said, "Ponce, I was impressed by your paper. I decided to hire you." That's the way it works. Okay, so because this is a paper that is totally different than routing. Routing was my expertise, and here is Ponce talking about something completely different, and to get it accepted in the ASCE journal is very unusual. They're very picky. They have turned me down a few times, actually. I think my batting ratio was about, I would say, 4 out of 5, which is lucky. A lot of people can only count with 1 out of 2. 80% of my papers were accepted. The other 20% were not for one reason or other. I have a lot of stories to tell you, but I'm not going to. But so the point is that I made a focus in here of albedo. I studied albedo extensively, and I tied it with Budico's model. Evidence linking increased surface albedo to decreased annual precipitation. What does that mean? The albedo of a rainforest is known to be 0.07 or 7%, while the albedo of the Sahara is considered to be 50%. So there's a marked difference in there that needs to be acknowledged. So albedo became very important. What is albedo? Albedo is the coefficient of reflectivity of the Earth, meaning, in my opinion, the most fundamental concept, because albedo determines everything on the surface of the Earth. If albedo is 0, you're going to keep all the energy. And if your albedo is 1, you're not going to keep any energy. All energy is going to be reflected and gone back to space. It's going to go from the sun and reflect it like if it were a mirror. So it is important. Now, the question, of course, from our standpoint is, what is the albedo of the Earth? In other words, how much energy is being kept here for various uses? And that we will get there. The mean planetary albedo is 0.34. The mean albedo of the Earth's surface is only 0.15. So about half. Why is that? Well, because the Earth's surface is a little darker than on the when you have the clouds. The clouds are going to whiten out a little bit the appearance of the Earth. So again, you can see in here, 0.34 is above the clouds and 0.15 at the surface. Actual values can range from as low as 0.07 for tropical rainforests to about 0.60 for hyper-arid deserts. That is true, and that is the range published in various books. Higher albedos are possible in the case of freshly fallen snow. You know that snow reflects a lot. We know that for a fact. One can get burned and if you stay in snow too much because the reflection. Okay. The mean annual, well, here I mentioned something very important. Global precipitation is around 1,030 millimeters. The precipitation falling on peripheral continental areas is 910, according to Leibovich. Because we're only interested in the precipitation of continental areas. We're not interested in the precipitation of the ocean. These values are spatial average. And I do not know exactly how Leibovich calculated his value. But I know that I have consulted various references. And the number that comes up continues to pop up as 800 to 830. I'm sorry, 850. And I decided at the time that I was going to use the number 800 because it is a round number. It is a Kabbalistic number. It is the cubic power of 2. It's a fundamental number. So we rounded the 910 of Leibovich to 800 of Professor Ponce's. Middle of the so-called climatic spectrum. What's the precipitation around the world? It varies from close to 0, such as in northern Chile, in the Atacama Desert, to extremely high values in a few isolated hyperhumid regions. For example, 11,270 millimeters per year at Cherrapunji, northeastern India. That is the place I told you I had intended to visit, and I couldn't for one reason or other in the year 1993, the end of 1993, 1994. That was almost 28 years ago. Unbelievable. Okay. The mean annual runoff coefficient, that's very important for engineering purposes. How much of the rainfall can we take advantage of? That is significantly influenced by the climate. Runoff coefficients range from near zero in typical hyper-arid regions to around 0.9 in certain hyper-humid regions. And that's documented by Leibovich. I believe the range of Leibovich is from 0.02 to 0.93 in the Philippines, and 0.2, I believe, somewhere very super arid out there. I actually believe that 0.2 is a practical number because in some rivers it should be much less than that. But I don't have data to support that from a global standpoint. So I think it would be best if we accepted Leibovich's data at face value. Runoff coefficients from 0.02 to 0.93. However, there's always a however. Values greater than 1 have been documented in some geological and geomorphological unusual settings. What am I talking here? Value greater than 1? That means more runoff than rainfall? And the answer is yes. There are some places around the world dominated by karstic formations. Karstic means the dolomites and such geology like that it holds a lot of water and then it releases the water. And there is a couple of places out there in Mexico, in the state of Veracruz, where there's a lot of these underground rivers or underground rivers. And there's one in particular that I have been able to document where the runoff coefficient was 1.19. And I have the reference. Of course, one could say, well, they made a mistake. They don't know how to measure. But that's not the case. They actually know how to measure. And they came up with that number. Very unusual. I had not seen any other case where the runoff coefficient is more than 1. Not that it doesn't happen. I know there's places, particularly in the southern part of Mexico, where this must be very common. Those are the places where you have the famous cenotes, which are the underground pools that they have all over the place in those areas. Okay, so here we're going to apply Budico's model. Let me say that what we have done in here is use Budico's model, present Budico's model. First, understand his model. And that's not an easy thing to do. But we did it. We were young and eager, I guess, and we put it all together. So we're going to be talking first about albedo and describe the various values of albedo. We did an extensive literature review at the time with our students. And we came up with this table. It's a complement of many, many tables that were put together in various places. Most of them are Eggleston's references, by the way. Eggleston was a professor. I don't know if he's still alive. He must be already in heaven because Eggleston is a generation older than I am. And I'm already old, so he must be out there in heaven somewhere. But Eggleston, professor, he wrote a very good book, MIT professor. And look in here, he is, we like him. We've referenced him extensively for the issues of what is the albedo. And as you can see, the darker the color, the lower the albedo. The lighter the color, the greater the albedo. Otterman has stated that the Earth's mean surface albedo might be presently 0.54. That's interesting. How can anybody say that? Well, Otterman in 1977 has said it. What he said was that it used to be 0.14 6,000 years ago. But he figures that there was a 10% increase in the time that has gone by. What does this mean? It means this, in plain English, that about 6,000 years ago, there was not a whole lot of development in the world. That after 6,000 years of development, the albedo has changed 10%, according to his estimate. He must have a way of estimating this. I can't second guess him. That is what he said in 1977. So we conclude that development as such can increase albedo, And the answer is yes, absolutely yes. Why? Well, let's backtrack a little bit. What is development? Development is a change for that society wants to do. Whatever society, you can talk about 5,000 years. The Chinese, apparently, that's reported in the literature, were the first to develop agriculture 11,000 years ago. And agriculture is already a change. First and foremost, the earth was covered with forests. And then climate change, and we don't know exactly whether climate change was anthropogenically induced or it came because it had to come or whatever. But there were changes, and eventually some of that forest was replaced by range. Then eventually the range was replaced by agriculture. And when would that have been? Well, it would have been when agriculture was developed in earnest. And like I already told you a minute ago, the Chinese invented agriculture 11,000 years ago, and subsequently they were already established as a society. The Egyptians could be like 6,000 years ago, the Mesopotamians in Iraq, then the Europeans. The Europeans don't date more than 2,500 years, the Greeks. And then after that, everything else, and we're already familiar with the history, more or less familiar with the history of different cultures around the world, different ways of how they consider development. In point of fact, development must have caused, every indication is that it caused an increase in albedo. It was only 10%. Why 10%? Well, there's increases, local increases of more than 10%, but not the entire world, entire surface of the earth was developed. So therefore, averaging the spatial value, according to Otterman, it comes up as about 10%. Albedo and climatic changes. How does precipitation occur? We already know that you have to have moisture, you have to lift it up so they will condense, and you gotta grow to sizes enough to precipitate, sizes large enough to precipitate. It's like a three-step process. The moisture has to come in, it has to lift, and it has to condense, rather not condense, but coalesce, and so it can precipitate. Otherwise, it would just stay up and will not rain, as we already know. So, this is a schematic of the model of the Budico model. Prior to Budico, our traditional way is you got the rain, it falls on the surface of the earth, it runs off, you can figure out what the ratio of the runoff is. It 30%, is it 50%, or whatever. But we were not considering a cybernetic concept. Now, in here we have a more complete description of how it actually happens. We have the advective precipitation coming from the ocean into the atmosphere. At this point, being held in the atmosphere, it can precipitate. But not all of it precipitates. Some of it can just look down and leave. And that's exactly the way it happens, because not all the moisture that moves into the control volume will precipitate. We know that already. Okay, so C plus, or C, not plus, C prime moves out there. Okay, then the precipitation gets into the land, and then from the land it evaporates. Ground evaporation, vegetative evaporation, water evaporation. We already talked about that. It constitutes one evaporation that gets in the control volume of the atmosphere. From there, the evaporation can follow one of two paths. It could recycle, or it could leave the premises. And if it does leave the premises, it joins C prime, C double prime, it comes back to C, and then the mass is conserved. The mass has to be conserved. There's not one molecule of water or of anything else that has left the Earth since the Big Bang, since they were created. So we come in here. So then, according to the Budico model, precipitation consists of advective precipitation and evaporative precipitation. And the issue is what percentage of these two in any one local situation. And that's the issue that we need to figure out here. In the Amazon, for instance, it rains a lot. It rains 3,200 millimeters per year, even though one could not say that there's a whole lot of moisture out there, but it does precipitate. Why does it precipitate? The answer is because it has a very low albedo. The albedo of the Amazon is 0.07. So that already explains the situation. In the Sahara is the opposite. There's no PCV. There's no recycling. Most of it left as C prime. It saw the land and it said, I want to rain here, and it moved out. So the assessments of how these numbers vary across the climatic spectrum is what we're going to do here today, following the model of Budico. And then I'm going to have you do some rough calculations as part of the homework. Charney was one of the people, one of the scientists that studied the drought in the Sahel. And I'm going to be talking about pointedly about the Sahel a few minutes later on. So Charney gets the credit for having extensively studied the drought, the 1970s and 80 drought in the Sahel. The drought in the Sahel went on to 17 years. And those of us that have studied droughts know that the droughts typically last 5-6 years if they're very severe, not 17. So 17 must be something extremely unusual. Okay, so this is Budico's hydroclimatological model. And like I said, I'm not going to go into the equations, but I want you to look at the equations. I did say this, that the precipitation at any one time or in any one space is going to be fraction derived externally, the P advective, and fraction derived internally from evaporation, from local evaporation. In other words, we could simply say that if in a desert it rains, once it evaporates, it's gone. If in a humid rainforest it rains, it evaporates and it returns. How does it return and why does it return? Because of the albedo. It is the albedo that's the major trigger to return the evaporation, recycle the evaporation. Okay, so I'm going to have you do the homework so you can review these equations later on. This omega parameter is the Entekabi parameter. Entekabi was one of the people over at MIT that worked with Eagleson, younger person. He could be of my age, roughly. Professor Entekabi at MIT published a paper in 1992 on this subject. They defined this omega parameter by, it's like a conceptual parameter that considers the mass, a balance of mass out here, of what's coming in and what's going out. And finally, at the end, we came up, based on all this, I decided to come up with water balance coefficients. We had experience with this because we had studied the Leibovitz method. We talked about that already. So we came up with the moisture recycling coefficient, the water vapor discharge coefficient, and the runoff coefficient. The runoff coefficient everybody knows, but not these other two. But we thought about it and we thought that we could put it together. And conservation of mass requires that these three coefficients add up to 1, and that's how it led us to the graph that I have shown you about 15 minutes ago. So the rest of here is just talk on the subject, and then we have the table. So I urge you to examine this table, and by the way, I've actually explaining in here how we did calculate this table. Yeah, right, it's right here, the calculation shown in table 2. This kind of calculation, by the way, is an unusual calculation. It has all kinds of constraints and stuff. It's not straightforward. I think that most of you, when you reach this study, and you're going to have to study it because I based the homework on this subject. You're going to see that it is unusual, not to say weird, but it is consistent and correct. We vary the climate types from hyper-arid to hyper-humid. Subsequently, by the way, 2 or 3 years later, we had to come up with a slightly different classification. Don't forget that we did this in 1995. And then in 1998, we had another project, and we had to do something different. And at the time, we decided to move from the center of 1,000 to 800 because we thought that it was a better number. Everything indicated that it was a better number. So, but by doing that, I had to come up with a more than hyper-arid. So I came up with super-arid. So in my new papers starting in the year 2000. We now have super arid, hyper arid, arid, semi arid, subhumid, humid, hyperhumid, and super humid. Why hyper and super? Well, the difference, it's one of tone. Actually, it's of language. Hyper it's a Latin root, while super is more like I guess you could say Anglo-Saxon root. But we use them both. Now, which one was supposed to be on top or in the extreme? I chose super. I can't tell you why, but I had to do something in here. I had to separate it. So we go from super to hyper, arid, semi, sub, humid, and hyperhumid, and superhumid in here. Why did we go semi-arid and subhumid? Why don't we go semi-humid? Because we didn't want to rock the boat. You should rock the boat a little bit, but not too much, because then they're going to kill you. Okay? So I left the subhumid. I had no problem with subhumid. But really, technically speaking, it should be semi-humid. That's minor thing, no big deal. Hydroclimatological impact, summary and conclusions. I think I already told you that it was from my PG&E study, 1989-1990, that I discovered environmental science, and I became an environmentalist, for right or wrong. So most of my papers that subsequently followed that have had some tone of defense of the environment. And this is what we were trying to do in here. We were trying to show and point out mathematically that we should control the changes in albedo. We should try to minimize, we should try to reduce. And by the way, this subject is already out and people are talking about it. Just Google albedo, and I'm sure that maybe 10 years ago there were probably 5,000, and now there's probably 1 million references to albedo in the literature. People are actively talking about albedo and its effect on the ecosystem. The Sahel. The Sahel is a fascinating story because, like I told you, they had a 17-year drought. Where's the 17-year drought? Let's take a look. We're here. This is the precipitation history in the Sahel to the year 2008. This is when we did this, by the way. We have not changed it. I'm sure that if you looked on the web, it probably has extended. All the graphs that have a certain time end up being extended by people that do research in the area. But as you can see in here, red is when it rained, blue it didn't rain. 1980, 1990, they have droughts. They had a huge drought in here. I'm sorry, not drought, the opposite of drought. Very wet period for about 10 years. That is interesting. But in here they had a sequence of floods and droughts, or wet periods and dry periods. They say that in 1917 there was a big drought, and this is that big drought caused a lot of famine out there in the Sahel. But over here, from 1970 to 1987, 89 I think, we have 99% of it blue color, meaning drought. So that's explained why is it that that happened. By the way, this drought in the Sahel is one of, that name doesn't sound good, no, Sahel, but it is Sahel. That's the name of it. I have not been out there, and I don't have plans to going out there. I would love to, but it's not in my things to do in the future or in the near future. Where is the Sahel? Right here. I pulled this off the web. It's an area. It's a geographical area. It's a climatic area. Why is it like that? Why is it a strip so narrow? The Sahel, comprising portions of 10 African countries, from left to right: northern Senegal, southern Mauritania, central Mali, northern Burkina Faso, southern Algeria, southwestern Niger, that's the name, that's the pronunciation, sorry about that. Northern Nigeria, yeah, that's right, central Chad, central Sudan, and northern Eritrea. Since it is a narrow portion, you can see that it only covers part of various countries out there. Countries have nothing to do with the climate anyway, at least the division of the countries. Now let's take a look at a map. There was also, I pulled this out of the web. I have no reason to believe that it is entirely accurate, but it is fairly good in terms of depicting what's going on in the Sahel. We have 200 millimeters 400 millimeters, 800 millimeters, and 1200 millimeters. That's the way they chose to plot it. So that means that the Sahara doesn't rain anything, maybe 100 millimeters, hyper-arid, hyper-humid, while over here, in this area over here, more than 1200 millimeters, that's already very wet. And I venture to say that over here, there must be a place where it's maybe not 1200, but 1600. That is the tropical rainforest of Africa, which is in this area, by the way, and somewhat limited in regards or in connection or in comparison with the Amazon rainforest. It's very small. I would say, roughly speaking, it's maybe 5% or something like this. But if you don't trust my numbers, one could go Google the difference or the difference in sizes between the Amazon rainforest and the African rainforest. So that is the Sahel. What's the big deal about the Sahel? Well, the big deal about this is that all hydrologists recognize that the drought of 1970, 1987 was anthropogenic. It had definite flavor of anthropogenia in there. So let's examine why. This is the way it looks. It's semi-arid. It has been abused because this is a gully. And you guys know that every time there's human abuse, it leads to gullies. Now, there's gullies out there that were there without human abuse. A connection, you could have a flood, or rather a drought followed by a flood. And floods and droughts are natural. So I'm not going to say that all gullies out there were human-induced. No, that would be wrong. But a large percentage of them, particularly in the areas that have been subjected to more anthropogenic pressure, those gullies are likely to be human-induced, meaning anthropogenic. The climate of the Sahel is arid and hot, with strong seasonal variations in rainfall and temperature. The Sahel receives 200 to 800 millimeters of rainfall a year, which falls mostly in May to September monsoon seasons. Rainfall is generally higher in the south, declining rapidly as one reaches the northern edge. Obviously, I already told you it's a strip. It's actually 4 strips. The rainfall is characterized by great variation from year to year and from decade to decade. Right. Why is that? Because in the middle of the climatic spectrum, there's a lot of variation, and half of it is in the middle of the climatic spectrum, determined by the movements of the intertropical convergence zone. Right there, they're getting very meteorological, global meteorology. There's a strong correlation between rainfall in the Sahel and intense hurricane activity in the Atlantic. I can't get into that. I don't know too much about it. This is all pulled out of Wikipedia, by the way. Okay. It can bring sand and dust storms. Yeah, some of it, pretty bad. Source Wikipedia. And finally, this is where I'm going to get here. Transhumans. Transhumans. That's a fascinating name. I had never heard of it, and before I came across this about maybe 10 years ago, teaching this class, I wanted to talk about with sense of the Sahel, not just to show a picture, but to say, how is it that this could have happened? So traditionally, most of the people in the Sahel have been semi-nomads, farming and raising livestock in a system of transhumance, which is probably the most sustainable way of utilizing the Sahel. What does that mean? The difference between the dry north, which is semi-arid, with higher levels of soil nutrients, listen to this, soil nutrients, in the wetter south, is utilized so that the herds graze on high quality feed in the north during the wet season, and they trek several hundred kilometers down to the south to graze on more abundant but less nutritious feed during the dry season. How fascinating. So does that mean that it's not just all water? And the answer, of course not. It has never been. It has never been. Water related to albedo, amounts of albedo, we already talked about that. The albedo related to vegetation. So it cannot just be water. It's vegetation out there. It's environmental. It's hydroclimatology, a subject that we decided to develop in the year 2014. I think I already talked about that already. But that's the difference. So what happened in the Sahel was that people were nomads because over the years they felt that was the best way to survive. So during the dry season, during the yeah, the weather's out. What am I saying in here? I'm getting confused. The north is dry, no matter what, but it has higher levels of soil moisture. So when it rained, they went up north, and when it was dry up north, they moved south. They moved 300-400 kilometers, and the herds grazed on high quality feed in the north, and then they moved down. They moved south, and they grazed on more abundant but less nutritious feed during the dry season or the dry period. How could this happen? And the answer is very simple now, not at that time, but it's very simple now. If there's a lot of rain, the amount of nutrients diminishes. Why? Because the rain's not selective. It moves everything out. If it doesn't move it on the surface, it moves it to the groundwater. So it turns out that the amount of nutrients in the soil of the rainforest is a low quantity, while the amount of nutrients in the soil of the arid areas is high because it has not been washed out or lixiviated or subject to leaching. It's called so-called leaching, lixiviation or leaching. So you see, you cannot have your cake and eat it. If it doesn't rain, you have a lot of nutrients. If it rains, you have a lot of water, but you have no nutrients. That concept is what led your Professor Ponce to develop my 800 millimeter isohyet theory in the year 2011, 11 years ago. And I briefly will talk about that later. Increased permanent settlement and pastoralism in fertile areas had been the source of conflicts with traditional nomadic herders. This is what Wikipedia says, and I don't disagree with them. I think it's possible. What am I talking about here? I'm saying that if you take those people that are nomadic and they are following the weather, so to speak, from year to year, and you tell them you shouldn't do that, you should stick to one place, they could do it if they follow your orders, but the environment is going to suffer because it's not going to be correct. They need to do this, and they've done it for many years. So this is what in Wikipedia and many other places is called transhumans. So the transhumans may or may not be correct from the environmental standpoint. The Sahelion Drought. There was a major drought in the Sahel in the year 1914. And then there was one in 1968 to 74. The 1978 led to large-scale famine. But this time the famine was tempered by international visibility and an outpouring of aid at that time. So there was not a whole lot of aid in the 1914 because there was not awareness, there's no television, and so on and so forth. You know, anything that happens around the world today, tomorrow we find out on TV. That didn't happen 100 years ago. Okay, so fascinating story of the Sahel, which relates very much to what we're saying in here. Is vegetation paying its own way? I'm going to shift here gears a little bit, and I'm going to follow the vector rather than the raster. The reason is because the raster is a little bit old, so I prefer at this point to follow the vector. So the question that I pose in here is vegetation paying its own way? Meaning, are we competing with vegetation for the water? Because vegetation is taking a lot of water. According to the design of nature, 70% of the water that rains is used by the vegetation, the ecosystem, so to speak. We can only count on 30%. And we're not even going to count to 30% because 10% of the total has to be reserved. Nowadays, it is reserved for the so-called environmental discharge. So we can only use 20%. But wait a second, 20% in a normal situation where the runoff coefficient is 30. But if you had a runoff coefficient of 20, then you only have 10% to use. To use where? To use everywhere. Every use of water that we have, water resources. If the runoff coefficient is 10%, if you want to use the 10% to sustain the ecosystem, the natural ecosystem, there's no water left for us because it's already there for the animals, for the fish, and for all these other animals. So where are we going to get the water? Oh, well, we can import it, right? And this is exactly the sense that has prevailed in California since it was founded. California was created in the 1850s, but it wasn't until the turn of the century that people started moving in large quantities to California, settling in California. mostly from the eastern United States, but eventually from all parts of the world. That is a fact. We forgot to realize that at the time that California depends on where you live. If you're in the south, there's no water. And if it's in the north, there's a lot of water. So people could move to the north and forget about the hydraulics. But no, that didn't happen. Why? Because people like to go to the dry areas. Never mind that there's no water. The state will take care of it. That's exactly what has happened. Over the last 100 years, California has imported a lot of its water from the north, where there's a lot of water and there's hardly any people. I already told you, out there, 20,000, 30,000 people is a town. Down here in the south, Los Angeles has 60 towns, 60 cities. And San Diego has 18 cities. Each city is about 50, 60, 70,000. Total population in San Diego is 2.5 million. And in Los Angeles, maybe 12, 13 million. By the time you put the population of the Southland, it's about half of the state of California. And it's only a portion of it, a fraction. Needless to say, that a truism is that people don't like water. We like the water to shower or to drink it, but we don't like it coming at us all the time. Why is that? And the answer is very simple. With water come all the bugs, and we don't like the bugs. We can't compete with the bugs. That's a fact. I can tell you stories about that, but I'm not going to. You already know them. Okay? My wife and I have been fighting the mosquitoes for the last couple of weeks. We finally got rid of them. But they were out here. They were visiting us and wanted to get a portion of us. I don't get to get into details, but it was pretty bad. I don't know if you guys have that problem. It can be solved. We had to call the guys that really know how to do it, and they told us how to do it. Okay, you got to get smart and outsmart the mosquitoes. But at any rate, and where? Because of the moisture. The mosquitoes go with the moisture, and there's moisture out here for whatever reason, the weather, the hot weather, and so forth. And so I'm not going to get into details, but I'm telling you that historically people like to settle the dry areas and not necessarily the wet areas. Now, if we had a choice, now, of course, look at South America. South America, 80% of the Amazon rainforest. The population in the Amazon rainforest of Brazil is 200 million people, and maybe 1 million at the most, or very little amount of people, not too many people in the rainforest. We know that. Look at this. It does not rain the same amount everywhere. We're going to finish in here. Something must make deserts different than rainforests. There's a desert out there. That's a picture from the Sahara and the rainforest out there. You have seen this picture before. What's that tree doing there? There must be water there. If there was no water in the underground and the groundwater, there would be no tree. That's called an oasis, by the way, because below that sand, all that sand that you see in there, there's water. There's a certain depth, there's water, maybe 10, 20, 30 feet, but there's water. Mainzer documented in his great book, 1927, that in the western United States, the average was 27 feet deep for the groundwater. But there's that some trees like the mesquite in Arizona could send their roots to 50 to 60 feet in search of the water. So the trees know what they have to do and they go after it. That's life, preservation, right? So we have in here two pictures. So the question that we have in here is, why does it rain more in a rainforest? Or better yet, why does it rain? Which leads to, how does it rain? So we're going to try to answer those today. How is rain produced? We have moisture. Atmospheric moisture varies within a narrow range. In humid regions, it's 45 to 50 millimeters, while in polar regions, it's 2 to 15 millimeters. So the moisture is 4 to 5 times greater in humid regions than in arid regions. Yet rainfall can be more than 100 times greater. Therefore, we conclude that moisture availability by itself does not explain the entire phenomenon. Condensation is very important. The easiest way for moisture to condense is through cooling, and nature provides various ways for moisture-laden air to cool. That is why there is so much precipitation. Global terrestrial average is approximately 800 millimeters per year. So there's 4 types of cooling. We granted that only by cooling can you produce rain. So how does the air masses on the atmosphere cool, on the lower atmosphere? First is convergence. The second one is frontal lifting. So in here you have an accumulation from all sides, and the air in there is lifted, like literally lifted up. Or you can have cold air coming into an area of warm air, and it comes because it's temperature, and it like wedging. It lifts the warm air up, and that's called frontal lifting. It's lifting due to a front of cold air. The third one is orographic lifting, the one that happens here in San Diego County. Here in San Diego County, at Lindbergh, we have 10 inches mean annual precipitation. Over here in Ramona, we have 15 inches. And over here in Laguna Mountains, we have 20 inches. Down here over in the Salton Sea, we have 2 inches. Why is that? Because all the moisture that came in here, it got wrung out, and it precipitated over here, thank God, and it didn't, by the time it went through the peak in here, there wasn't any moisture left. So and it sank, by the way. And when it sinks, it warms, and therefore it wasn't going to precipitate. That is the California desert, where the Salton Sea is located. Not too many books talk about this fourth lifting, which, by the way, was extensively the subject of what Balick wrote in his book. That's why I'm telling you that my meeting with Balick was extremely important. Again, very much coincidental that I was there at the same time he was there in India. Roorkee, by the way, at the National Institute of Hydrology. Thermal lifting. Thermal lifting happens because of albedo. When the albedo is low, it produces heat. And the heat over here on the surface has no other way to go than above. And it produces the so-called thermal lifting. So we are forced to conclude that if we didn't have any of the three, we can handle the fourth one, thermal lifting. And this is exactly what happens in the Amazon rainforest and all the other forests of the earth. I'm talking about the Amazon because I'm familiar with it. But there's not as big, but there's many forests out there. What differences between the temperate rainforest of the United States, for instance, and the Amazon? Theoretically, the temperate rainforests don't generate as much water because the albedo is higher. The albedo of a temperate rainforest may be on the order of 0.15. Amazon rainforest 0.07. There's a lot more heat and a lot more water. Not to say that it is the maximum. We know for a fact that the tallest trees in the world are here in Northern California. They're about 80 meters, 250 feet high. How is it that the trees in the Amazon are higher than the trees in the Amazon rainforest? Simple. In the rainforest, it only rains from 22 to 3200. In California, in the triangle out there, coastal corner triangle out there, I don't know the exact name of that region, but you understand what I'm talking about. It rains so much that it gets to be on the order of 48 to 5,000 millimeters, double the amount of the Amazon. The trees don't get up to double the height. They only get up to a little bit, 20, 30% more. But they are bigger. The Amazon, the California trees are extremely huge. There's a couple of them that are out there, the largest by volume and height, because height gives the volume. It gives the volume. Not all the time. It depends on the volume, obviously, right? But we know for a fact that there's a couple of trees here in California that are considered to be the largest by volume. One of them in that triangle that I was telling you, the northwest triangle of California, Northern California. Okay, albedo. We already talked about albedo. Vegetation produces its own rain. Yes, positively. Vegetation brings its own rain because of the albedo. Vegetation brings its own water and pays its own way. So, if short-sightedly, we, meaning society, are envious about the water that the vegetation is taking and want to steal it, we can't. Because once you kill the trees, you're killing the water too. The water will go away. The albedo will change. You will change a forest with a desert. That's called desertification. It has happened and continues to happen throughout the world. Yes, now we know. Albedo and anthropogenia. Of all the factors that contribute to the formation of precipitation, none is more subject to anthropogenic alteration than surface albedo. Belatedly, we have realized that we may have caused rain decreases by replacing forest for range. How about that? Range for agriculture and agriculture for urban. Yes. So every step of the way from development, there are 4 steps. Forest to range is the first step. Range to agriculture, second. Agriculture to urban, third. And every one of these phases or moves resulted in the increase of albedo. If we tamper or otherwise reduce or eliminate vegetation, we are tampering with the hen that lays the eggs. Sustainable strategy must be predicated on ecosystem preservation and conservation. So ecosystem preservation and conservation is like fighting global warming. You could fight it in 2 ways. You can fight global warming in 2 ways. And it's a very well-recognized fact. Not increasing the amount of fossil fuels that are being pumped into the system, or increasing the amount of trees and nature, ecosystems that have been subject to use and much abuse over the last, I would say, 100 years. It's been over the last 100 years since really humanity in earnest has decided to develop. And that development has caused problems which we are only now understanding how or why is it or how is it that they were produced, and therefore we must do something about it. And this is ongoing, by the way. But it's only beginning. Returning to pristine conditions is panacea, meaning it's unattainable. The best we can do is to stop the process of increases and consequent gradual disappearance of the water resources of the earth. We reckon that climate change is also possible in a regional context. Right. Climate change is global, climate change is regional too, sure. Epilogue, and I'm going to finish here, I got 2 minutes. The vegetal and animal kingdoms are equal partners, as they have been so since the beginning of time. Vegetation helps produce the water that we use for drinking and bathing. Vegetation does not compete with animals for the water. If that had been nature design, the world as we know it would have climbed and fallen prey to a J-curve long time ago. J-curve is the opposite of cybernetic. It goes up and you can't control it and it gets destroyed. Instead, the cybernetic functioning of the biosphere assures that all components work in unison, complementing each other to assure sustainability. Sustainability is a big word, but a word that we only discovered 30 years ago. Actually, roughly 30 years ago, 1987. The word was coined in 1987, sustainability, in the context of what we should do to sustain the world. Enlightened societal strategies must stress preservation and conservation. Otherwise, deserts will take over eventually, and our precious water resources will all but disappear. And it has happened in many places throughout the world already. And I will see you in class 062 this Wednesday. And it will be the same subject. We have 2 weeks covering various topics in hydroclimatology. Thank you. Bye-bye.